spontaneously. And when reaction happens spontaneously, that means it results in producing energy. So that's the beauty of this whole step. Every step produces a positive E value. And that positive E value is equal to, you can do the calculation and convert to free energy. And the free energy is what is driving the process forward. Ultimately leading, I'll get to that slowly, to ATPase protein, which is Q5. And that is where the synthesis is going on. ADP is getting converted to ATP. So that's the whole process. So again, I don't want to really get into the details about this because you won't follow it. So let's just just leave it at that. Just say the electron transfers from one protein to another, resulting in a reduced form, giving you energy. I'll leave it at that. Okay. So what are the results of Q cycles? So when you have a conversion from QH to Q, for example, you have these transfers going on. 2 electrons from QH to reduce 2 molecules of the protein, right? So this is so in this process, now we are talking about the energy that is produced by this protein in each step has to be used somewhere, right? And that energy is used to basically pump the proton outside mitochondria. And remember what I said about the inner membrane of mitochondria? Inner member of mitochondria is so non-porous, meaning nothing goes through it. So even to push the protons out, you need energy. It will not happen on its own because it's not porous. It's very selective what it allows it to do. So all the energy that is generated is used to push the proton outside matrix. Matrix is the inner mitochondria to outside. And that energy that is conserved is basically used for that purpose. So what happens is, in this process, you push, let's say, 4 protons are pumped out of the matrix. So in this step, all the energy that you have generated, that's what happens. So 4 protons are pumped into the intermediate space, which means you have a mitochondria inside, you have an inner membrane, intermembrane space, and then you have an exterior membrane, right? So those are the, and so inner membrane is the one that is very non-porous. Nothing goes through it. Even if you have to push the protons out, you need the energy to do it, right? So 4 protons are pumped into the intermembrane space. 2 are from QH2 in the first round, and 2 are from QH2 in the second round. So that's altogether 4 protons are pushed. Now you go into complex 4. Again, I'm not going to go through in detail as to what happens, and you can follow it here. But here again, cytochrome C, iron 2 plus, is getting, in this case, oxidized. So it's going. So the energy that was saved in the reduced form is getting oxidized, Fe2 plus to Fe3 plus. But what is happening here is, in this step, you have oxygen is getting reduced to water. And so that's the reaction in this case. You have 4 protons are again getting pushed out, and basically your oxygen is getting converted to H2O. So if you look at in your textbook, right, one of the reduction potential reaction was oxygen getting converted to H2O, and that's got a very positive E value. So that's a highly favorable reduced process when this happens, right? So this produces obviously energy when you go from here to here, and I'll do that calculation for you as to how much energy is generated in that particular step, and I'll do one problem based on that. But let's just go through and finish these steps off, because there's plenty of stuff to. And again, I'm not going to really ask you anything about the structures and stuff, but this is again for the complex 4, which is called cytochrome C oxidase. I won't ask you for the names, just complex, just need to know how many protons are pushed, that's all. I'm not going to ask you anything about the names of these enzymes. And I won't ask, just know them as complex 1, complex 3, complex 4, that's enough. And I won't ask any details on it, but just for your own knowledge, the way these proteins are, see how this protein is buried inside the membrane. This is membrane, bilayer membrane, and then you have stuff sticking outside matrix and stuff sticking on the other side. And so all the reaction is going on this side, on the matrix side. So on the surface of this is where all the reaction is going on. So this is complex 4.
It's happening in the matrix?
Everything. So let me reiterate. Every reaction that is happening in this oxidative phosphorylation is happening inside the matrix. Not only that, every protein is attached to the membrane. which is not the same as citric acid cycle pathway. In citric acid cycle pathway, the stuff is happening inside the mitochondria, but not every protein is attached to membrane, except with the exception of Q2, right? The Q2 is the only one that is attached, the complex 2, that's the only one that is attached to the membrane in PCA or citric acid cycle pathway. But when it comes to the oxidative phosphorylation or electron transfer chain reaction, ETC, everything is attached to inside of the matrix, right? So let's keep on going. All right, so anyway, again, I'm not going to ask you anything on this, but this is really showing you as to how the oxygen is reduced to water. These are the steps if you're counting as to what happens to the oxidation state of, this is basically iron copper complex protein, and I'm not going to ask you anything on that in terms of what happens in terms of the process. Only thing is that's the proposed mechanism. Don't really worry about the mechanism. Okay, so the main thing is, so in this case, the total number of protons that are pushed out here are 2 protons in this case. So the 2 protons are pushed out with the energy that is generated. So, and all together, let me just tell you, 2 plus 4 plus 4, all together 10 protons in the whole process are pushed out. So all the energy that is generated is based on every step, and you can please read your textbook as to where that is important to know which step the electrons are being pushed out. Just do a quick read of your textbook and you'll get a good idea where the protons are being pushed out. So that you need to know. But in total, 10 protons are basically pushed out of the matrix into the intermembrane, which is outside the matrix. Anyway, so let's go and do the. All right. So with that said, how much energy is available for electron transport? How much energy generated? So if you are looking at each of these steps, right? So you have complex 1, complex 3, complex 4. 4 protons being pushed out, 4 protons being pushed out, 2 protons being pushed out. All these are basically the steps where the electrons are getting pushed. And the total energy that is possible is, if you add up all those 3 things, the Q2 really is not counted as a step, but that's more pooling all the stuff, right? So all these are the basically main oxidative phosphorylation, electron transport reaction, and the total energy is minus 218, and this is the energy that is used to convert ATP, to basically convert ADP to ATP. Now the way it does it is a little bit different, and I'm just going to quickly mention there's something called proton motive force, meaning this energy that is generated is saved by pumping the proton outside the matrix. And what that does is it created 2 things. It creates the charge potential, and it creates the it creates the concentration gradient. Because see, if you push the protons out, you'll have a different concentration of protons. And also because you have different positive and negative charge, you'll have a charge potential. So those 2 things is what drives the process forward. But basically energy is energy. It's being saved in some form. And that's how it is being saved. All right. So, yeah, please go ahead.
All right. Complex 1 had 4 protons, complex 3 had 4 protons, and complex 4 had 2 protons?
Yes. So these are the steps, right? So this is complex 1, complex 3, complex 4, right? And so this is what is showing. See how it is, initially you have positive protons inside. They're getting pushed out, right? And that generates the extra positive charge outside. That means the pH would be lower here, and pH will be higher inside the matrix. Because the less protons, it will be more basic, right? So there will be more basic pH inside the matrix, more acidic pH outside the matrix. And I'll show you, it will make more sense as to what are these protons doing. Actually what happens is, these protons are actually entering back through step 5, and that is what driving the protein in that step. I'll explain that and maybe it will become a little bit more clearer. But the whole point is this proton pumping out is what the energy is saved as. And this energy is used in step 5 to produce ATP. Okay, so this is those 3, and so the main thing you have to know is this is what is called the proton motive force. This force of proton moving out is referred to as proton motive force. or in terms of the theory, please, as I said, I do want you to read for this chapter your, the little bit of chapter because I'm not really getting time to explain in detail everything, but read the proton motive force and chemi-osmotic theory. That's what it relates to. So just read the definition of chemi-osmotic theory in your textbook. So essentially it is the same idea. Chemi-osmotic theory is based on the concentration gradient difference and charge difference. That's what the chemi-osmotic theory was proposed, because the idea was somebody proposed it how the energy is being saved, and is being saved in the form of proton motive force, which theory was referred to as this chemi-osmotic theory. Okay, so just want to please read that. As I said, I don't have time to write everything on the board, unfortunately. So I want to spend time on doing the problem. So let's go ahead and do this. So again, what you need to know delta G is equal to RT, natural log, the concentration that is outside the out means outside the mitochondria, right? And in means in the matrix, right? Inside the matrix. So this is the concentration in the matrix. This is the concentration outside the matrix, which is in the intermembrane space or in the cytosol, same thing. So and the delta G is also equal to, so this is based on the concentration gradient difference, the difference between the concentration of inside and outside the matrix. Then you worry about what is the electrical imbalance, which is positive versus negative charge between outside and inside. And that is calculated based on delta G is equal to Z. Z is the charge, and in this case the charge is H plus, right? That means Z will always be equal to 1, right? What is the charge on proton? H plus. So the charge is, so Z value will always be 1. F is a Faraday constant, which is a constant which is given to you, and this is the potential difference. And I'll do the problem on that basis. And so the total delta G for it would be based on the concentration difference plus the charge difference, right? And so we'll solve a problem on that basis. Let me actually go ahead and do that. And let's do that and do the last part after that, which is, okay, so let me go ahead and write this. Okay, so let's do this. Let me use a red pen. Okay, so calculate the free energy change. Calculate the free energy change. And please memorize this equation because I'll definitely ask you a question on it. So just memorize that delta G is equal to RT, natural log, this plus ZF. And I'm solving a problem like that right now. Calculate the free energy change for translocating a proton out of mitochondrial complex where pH inside the matrix is equal to 7.8, right? The pH inside will always be higher, it's more basic. So inside the matrix is 7.8 and pH inside cytosol. And remember, the pH outside the matrix, which is the, so if you have, see, okay, let me show you. So this is the matrix inside, right? And this is the intermembrane space, right? And then you have a membrane here, and you have a membrane here, and this is cytosol. Everything can go through this outside membrane, right? Nothing can go through inside, but everything can go through. So whatever is the pH inside the intermembrane is the same pH as in the cytosol. All the protons can freely diffuse through, right? So that's why even when it says cytosol, right, that is same thing as outside matrix. It could be intermembrane space as well, right? So that's why it's confusing when they say cytosol, because the outside membrane of the mitochondria is very porous. Protons can go easily in and out. It's only the inside of the this one, the inside, this inner membrane, That is the one nothing can passes through. So the pH will be different here, and the pH will be different outside. So pH in cytosol would be 7.15. Okay. So so we are asking to figure out what is the delta G for this when this is the pH. So how do we do that? Let's go ahead, and you are given the potential difference, which is membrane potential. Membrane potential is given as 170 millivolt. This is from your book, this problem, so I'm going to use the same value, 170 millivolt, right? So we're going to use this equation, the one at the bottom, and let's go ahead and solve it, and then we'll do the last part after that. Okay, so delta G is equal to RT natural log the proton, which is outside the matrix, and the concentration of proton, which is inside, plus membrane the charge, which is Z, Faraday constant, which is a known, we will give you that, and you already know what the membrane potential is. So that's the equation you need to know, memorize it, because there will be a problem on that. So make sure you know this. So let's go ahead and solve this. So you're given a pH, right? At this stage, if you're given pH, you should be able to figure out the proton concentration, right? Because pH is equal to minus log of this. This is the equation you remember. You have, if you don't know, you should know this. And if you want to figure out the concentration of proton, then that would be 10 to the power of minus pH, right? That's how you figure out. So if you want to convert this from log to what would be the concentration of proton, then the constant proton is equal to 10 to the power of negative pH. So we can use this equation, right? Because we need to plug that in. So we can do this. We can just go ahead and delta G, I'm going to go ahead and solve. R is a constant which is given to you, which is 8.314 joules per Kelvin per mole. And the temperature we are going to use would be standard in this case. We'll do times 298 K. And natural log, and I think this is under standard conditions, or we can just say at 298 K, so I can give you a temperature here. The temperature is 298 Kelvin. So, okay, so we can do this. The pH is what for the outside? 10 to the outside is cytosol, so that's the 10 to the negative minus 1.5, right? So we can just simply say 7.15 because the proton concentration outside would be equal to 10 to the negative of the pH, right? So 10 to the negative minus 1.5, that's the pH that is given for outside matrix. Inside the matrix it is 10 to the negative 7.8. That is the pH. That is inside the matrix. Then plus Z. Z is 1. That is the proton is plus 1. So the charge is plus 1. In fact, for all these problems, you're only pumping the protons out. So unless there's difference, in this case, it'll always be 1 because we're talking about proton pumping, right? So it has to be plus 1. So so the F is 96,485 joules per volt mole. Okay, the main thing you have to remember, that is given in millivolt, right? You want to make sure units cancel out, and because this one is in volt, right? So you must always convert millivolt or whatever the volt is given to volt, because you want to be able to cancel this, because the constant is given in volt, right? So you must convert your units to volt. So in that case, what is the volt given? 1?
0.17.
Okay, so we will convert that to, so that would be that would be equal to 0.170 volt, right? So we can do that. Sorry, a little sloppy here, but this goes 0.170 volt, right? So this goes right here. Sorry, I ran out of space. So volt and volt gets cancelled, right? The K and K gets cancelled. Only thing left is joules per mole on both sides, right? And so if we do this, you're going to end up getting, if you solve this, you're going to get delta G is equal to 20,111 joules per mole. And you can convert this into kilomoles, that would be 20.111 kilojoules per mole. That would be the answer. Now I know in your textbook, I don't know if you, I like to solve it this way, but what they have done in your textbook, if you ever notice, they have converted log to natural log. So they have taken the same equation and they have converted to, and I don't know how much math you know, but if you convert natural log to log, you have to multiply it by 2.303. That's where that number comes from, right? But I don't want you to get confused. Why don't you just use natural log? Because your calculator can do natural log as easily as regular log, right? So I like to just show you this way. That way there's no confusion. Because in the textbook, if you look at the same problem, they have converted this natural log equation to log equation. So you can basically write the same equation. If you wanted to write it as a log, what you have to do is you have to multiply it by 2.303. And rather than writing natural log, that becomes log, right? That's the only difference. But I would just do it this way, the way I showed you.
It doesn't matter if we leave it in joules or kilojoules?
It doesn't matter. As long as the answer is correct, it doesn't matter. Generally, the delta G is reported in kilojoules, but it doesn't matter to me. As long as the answer is correct, you can do it in either. Yes, please.
Are you going to give us a question that's going to be either electrical imbalance or chemical or
It's going to be like that. So just, I'm telling you, I'm giving you a hint. That would be like, at least you should have some pleasure of coming here today. So,
It's always like that. It's always going to be in standard conditions.
say that again.
It's always going to be in standard.
298. If the temperature, okay, this I've been saying before, the temperature is not given, assume it 298 Kelvin. Right? So, yes, so if the temperature is not given, work under standard temperature, yes.
When would it be, like, how would the thing be worded into you doing it into pH equals negative log H plus?
Say that again.
So, like, you know how we're using the 10 to the power of negative pH
Yes.
to find the protons? So would it ever be reworded into using the negative log?
No, I mean, I guess it doesn't really matter. Either I give you pH, right? Or I directly give you the concentration of proton. That would even be easier, right? So
you just plug in the ln.
yes, so for example, right now I gave you pH, right?
Uh-huh.
So you had to convert it to the concentration of protons. What if I just give you the concentration of proton directly? Then you don't have to do the conversion. So
Okay.
you have to still understand the concept.
Okay.
Right, so it can, so yeah, I mean, the only reason I had to do that because I had given you pH. The equation is this one, right? Or you can write up this equation differently. How can you write? You can write natural log 10 to the power of minus pH divided by 10 to the power of minus, it's the same thing.
Yeah.
Either you can write it as, but if you write it as proton, then it will be like that, right? If you write it as pH, then you have to write it 10 to the negative minus pH divided by 10 to the negative minus pH of this, right? Is everybody on the same page? Okay. So, anyway, so that was the thing. So that's how you solve that. And I know if you use the natural log to log, you'll get the values slightly differently. Don't worry about it. But I would just do natural log. Don't try to convert it to log. As I say, you have on your calculator those values anyway. So so let's just go a little bit further, right? So this energy, 20.11 kilojoules per mole, is for how many protons? 1, right? So that's not the total energy. Remember the energy was 200 something, right? I said when we totaled up all the energy was 200. So if you multiply this number by 10, that will give you the total energy that is used, right? So so this is just for one proton. Calculate the calculate the free energy for translocating a proton, meaning for one proton. So if it was asking you for the whole thing, then what do you have to do? multiplied by 10, right? And that would make sense because if you remember when I added up those delta G values, right? It was around 200, right? So this is, I'm going to write this here, 20.1 kilojoules per mole for one proton, for pumping one proton. That's how much energy you need to use to pump one proton, or that's how much energy you will produce, the other way to look at it. So for 10 protons, therefore, it would be 200 kilojoules. So that would be for 10 protons, right? So just to, and that makes sense. When I added up all the Q1, Q3, Q4, it was approximately 200 some number, right? So that's how, so all the energy is saved in about, and some energy is wasted, right? But about 200 kilojoules is available by pumping 10 protons. So one proton gives you 20, so 10 protons will give you that, okay. So now let's talk about the last step in last, whatever time we have. We have half an hour. Okay, let's see what. It won't take me that long. I cannot answer any questions at the time is left over. So this is very complex protein. This is the last step. This is called ATP synthase. That's the name of the protein, and sometimes is also referred to as complex 5. It doesn't have any quinol or anything. The other ones are called Q because they are related to quinol. This one doesn't have anything like that, but it's called complex 5 just because it just comes in 1, 2, 3, and it's the last step. So you can either call it the ATP synthase step or the complex 5. That's the name of that this enzyme. But the actual name of this enzyme is ATP synthase. Okay, so ATP synthase again is a very complex protein. And this is the one that actually synthesizes and converts ADP to ATP, and I'll show you how it works. So all the energy that is utilized, and so this essentially is the enzyme that catalyzes the conversion of ADP to ATP, and it uses this electrochemical gradient, right, which I talked about. The gradient is concentration gradient plus the charge gradient, right? So that together is referred to as motive force, proton motive force, or chemiosmotic theory is based on that. So anyway, with that, you have this is the whole protein. This part is called F1. This is called F0, which is inside the membrane, embedded inside. And I'll just show you how it works, this protein. All right, so the way it works is you have the protons actually are able to bind to this particular protein, and essentially the way it works is this is almost it works in a sort of a cyclic way. So this protein basically keeps on moving, going around and around. As it goes around and around, and I won't ask you too much detail on the mechanism, but let's conceptually understand this is what happens. As it rotates, it changes the conformation of the protein. In one conformation, ADP can bind to it. In another conformation, ATP can bind to it. So it changes the conformation as it rotates. And every three of these rotation actually results in synthesis of one ATP molecule. So if this C goes from here and ends up here, that's 3 times, then that's synthesis of one ATP molecule. I'll show you how it works on the following slide, how it matches. Don't worry about the structure, but let me just show you. This is what happens. So this is almost like a cyclic, it's like rotating like a wheel. And so what happens is, first thing that happens, it has got this open binding space. ADP comes around and binds to this protein, and then it rotates. In the next one, the ADP is bound to this protein already, and then moves again, and then ADP gets converted to ATP, and well, first of all, ADP binds, right? In the first place it's open, then ADP binds to it, then ADP gets converted to ATP on the protein, then it moves again, and then it's not able to, in this conformation, it has no binding to ATP. So essentially, in this 3 conformation, which is called open conformation, tight conformation, and loose conformation. So the open conformation means it is basically open to accept ATP. Tight conformation means it is basically binding ATP. And loose means it has no binding to ATP. So in this whole cycle, as this goes through, as this rotates through, you go through basically open to, this keeps on rotating, and every time it rotates, it has an ATP molecule bind. 3 rotations later, you have an ATP released. And essentially this happens over and over again. And remember, in this whole cycle, and this ATP synthase is different for different organisms. So for example, in this particular case, you have 1, 2, 3, 1, 2, 3, 1, 2, 3. It produces approximately less than 3 ATP molecules. So because every 3 of those yield 1 ATP, and actually it translates to about 2.7. If average 2.7 ATP molecules in this, and the bacterial ATP synthase is different, human ATP synthase is different. So there's a different number of ATP molecules produced based on which organism you're talking about, right? But in this organism, the way it is shown, 3, 3, and then 2. That means it translates to about 2.7 ATPs being produced due to this rotation. Okay, so let me just mention this. Hold on. So what I want to do is, let me write down the definition for you for the chemiosmotic. Since I have the time, for the chemiosmotic theory, I want to write the definition on the board, and then I'll tell you about this slide, and then I'm done. This is the last slide, by the way. So then I'll tell you what this slide means, and then we are done with the class. So let me write down the definition of chemiosmotic theory. So you can write this down. So scientist Mitchell's chemiosmotic theory, and I'm going to write this down on the board. Okay, so this theory basically states that proton translocation generates a proton gradient across the membrane. This is because the protons cannot diffuse So remember, the protons are being pushed out, right, by mechanism, and they cannot diffuse back. And the way they come back, by the way, is through ATP synthase. So I'm going to write this down. The protons cannot diffuse back, meaning they cannot come back inside the mitochondria just by itself, right? They cannot. That's what diffusion means. So they have to go through some protein channel. They cannot just straight diffuse back into the matrix. So the protons cannot diffuse back into the matrix. Because, as I've been saying, because the inner membrane is impermeable, meaning nothing can really go through that. Permeable. Nothing can penetrate through it without any energy cost. So it's not permeable. It's impermeable to ions. So protons cannot just come back on its own. The imbalance of protons represents a source of a source of free energy, which you just saw in a problem that we did, right? How much energy was generated. This is also called a proton motive force. This force that we talked about is called proton motive force, or PMF, right? That's proton motive force. This imbalance of protons, that's what is referred to as. So this PMF, the PMF can drive the activity of ATP synthase. The enzyme that I just showed you, which is the complex 5, it is driven by basically proton motive force, activity of ATP synthase, which is complex 5. So this is really what the chemoosmotic theory is, which essentially shows you the point that I just made. So this protein, ATP synthase, catalyzes the conversion of ADP to ATP, right? I showed you that basically how ADP binds, it gets converted to ATP. So basically, just to show you how that works, right? So each of the each of the 3 cycles, right? When it's complete, it produces 1 ATP, right? However, remember, every of those C's get a chance to come in that open position, and so pretty much each C will represent actually 1 ATP. Maybe I didn't explain it correctly. It has to go 3 times to complete the cycle, but each of them gets a chance 1 time, right, to be in open position. So each C will give you 1 ATP molecule. So let me write this down so there's no confusion. So 3 ATP molecules. So 3 ATP molecules are synthesized for every complete C ring rotation. So the point here that is the number of proton translocation which is pumping out, the number of translocation of ATP depends on the number of subunits, or number of C subunits. Okay, so mammalian ATP synthase, mammalian, which is us, right? Mammalian ATP synthase has 8 C subunits. So the stoichiometry is based on how many protons. Stoichiometry is 8 protons for every 3 ATP molecules that is synthesized. That means it's 2.7 protons per ATP. That's so now let's get to this. So this is based on the only thing I wanted to mention here that this P stands for how many ATPs are there, and O stands for how many oxygens are being used in terms of oxygen being reduced to water. So the reaction that you have is here is this is the reaction. Oxygen getting based on 2 protons, 2 electrons, and is getting reduced to H2O. So for every 2.7 protons, you have a ratio between for one oxygen atom, right? You have 2 protons and you have 2.7 protons per ATP. So if you have, for example, say if you have 3.7 ATP, and I'll just count this. I'm not going to ask you anything on that. I just want to show you this slide in terms of what the ratio means. And the importance of this ratio is essentially how much ATP your body needs. So if the ratio goes down, then basically the ratio has to be brought back up in order to increase the synthesis of ATP. That's kind of a basic purpose. So if it's 3.7 ATP per half oxygen reduced, so for this, so the ratio is, in this case, 3.7 phosphorus to oxygen ratio. Phosphorus stands for ATP, O stands for oxygen atom. So I think I'm not going to focus too much on it, but basically the concept of this slide is that if you have a PO ratio, right, that is too low, then the more ATP has to be synthesized, and the ratio is too high, then less ATP has to be synthesized. That's really where I want to kind of stop, because I don't want to spend too much time on this. Okay, so let's just stop right here.